Today, we want to keep looking at double integrals. Remember, the big idea with integration is that we're doing multiplication, but one of the factors is variable, a continuously variable. Before, we had calculated, in Calc 1 or Calc 2, you calculated volume as area of the cross-section multiplied by the height. In that case, you made the area of the cross-section the function and the height the delta variable. Now that we have the technology of the double integral, we can switch things up. We can make the height the function of two variables, and the area can be the delta variable. That's the switch that we're making here. The technology that we needed to do this was the double integral. We needed some way to describe what values of x and y to plug into our calculation f at xy times dn. And so we came up with this scheme where we say what's x between and what's y between. And that's the game that we want to play. So this is getting more complicated than our single variable problems, because we're always just plugging in an interval, start at A, end at B. But now that we have dA being an area, we have to describe what values of x and what values of y to plug in. So with double integrals, we can describe the values that we want to plug in. With this in mind, anytime we're trying to describe a region for an integral, we should always try to do it both directions, dy dx and dx dy, to make sure that we understand the process. The other thing that we found out is that the integral over r of 1 dA, we just use 1 for the height function, then that'll tell us the area of the region. So the other thing that we have is that the integral over r of 1 dA is the area of r. All right, let's describe some regions. So here's our example for today. I'm going to take the rectangle from 0 to 3 on x and from 0 to 9 on y, and I'm going to divide it, but not with a line like we did yesterday. I'm just going to draw a parabola, and that's going to divide my region up. So I've got a region above and a region below. So I'm going to call this one up above, we'll say that's R1. And then down here, we'll have a region R2. Let's set up a double integral describing what's going on in R1. So we need to set up a double integral. We need to do this a dy dx and a dx dy. We're going to do both. We just got to pick one to start. I'll start with dy dx for reasons. So let's do a dy dx. If I recall, dy was in orange. And dx was in green. Easiest to start with the last integral, because that one has to be constants. And the x values that we are in between are from 0 to 3. So the x's are going to go from 0 to 3. Next, we want to pick a particular x value and see what values y is between. Notice that the y's don't start off at 0. If I pick a generic x value, I don't get to the region until I get to this parabola. And then I stop when I get to this line y equals 9 at the top. So those are going to be our two y's. Y is going to start off at x squared and stop at 9. So we pick a typical x. Once we establish that x's are going to go from 0 to 3, pick a typical x and see what y is between. Any questions? If we think about what this would look like if we just start integrating it, the first integral we would do if we wanted to integrate 1 to see, if we want to use the integral of 1 to find the area of the region, we can see that that's what we're going to get. If we integrate 1 dy, that gives us y evaluated from x squared to 9. So we'd be integrating from 0 to 3, 9 minus x squared, which is exactly going to be the area that we're looking for. Because we take the top function, 9, subtract the bottom function, x squared, and that will give us that area of that top region. So it looks like it's going to work. Let's set up the other integral. Let's set up a dx dy integral. So now the x's can be between functions of y, but my y is going to be between constants. The y's have to be between constants because that's going to be my last integral. And the y's go from 0 to 9. The lowest y value that we'll have is 0. And the highest y value we'll have is 9. Now we just need to pick a typical y value and cover the region. What's on the left and what's on the right. So at a typical y value, looks like the x's start off at 0 and end at the parabola for region 1. So on the left, we have an x at 0, and on the right, we have the parabola. Since y is equal to x squared, we can solve x squared, y equals x squared for x, and write x equals the square root of y. So in the y direction, we start off at 0. In the x direction on the left, we have 0, and on the right, we have square root of y. If we think about integrating the function 1 to find the area of this region, when we integrate the function 1 dx, we end up with x evaluated from 0 to the square root of y, which gives us the square root of y. So we're looking for the area under the square root of y between 0 and 9, and that is exactly the area that region 1 encompasses if we just look at it sideways. Questions? Now we want to do the same thing for region 2. We want to set up two integrals, a dy dx and a dx dy. So we're going to want a dy dx and a dx dy. So for region R2, let's start with the dy dx integral. Dx is the last integral, so that's the one that has to be the constants. And as far as constants go, x still goes from 0 to 3 for region R2. So x still goes from 0 to 3. So now we're going to pick a typical x value and see where the y value starts. And now if we pick a typical x value, we can see that we start off, the y starts off at 0, and the highest y is x squared. So the y's will start off at 0 and go up to x squared. Integrating 1 to make sure that this fits in, make sure it's backwards compatible to the stuff we had before. This is just an area problem if we integrate the function 1. The integral of 1 dy is y, evaluated from 0 to x gives us x squared. So our integral is from 0 to 3 x squared dx, which is going to be the area under the curve, x squared from 0 to 3. So it looks like that's going to work out. Now let's do the same thing with a dx dy integral. Just like before, the lowest y is 0 and the highest y is 9, so the y's go from 0 to 9 as constants. But now we have to describe left to right for a typical value of y, the x's. And so now in this case, if we pick a typical y value, we head over to the region R2. The region R2 starts when we hit the parabola. So it starts when we hit x equals y, square root of y. And it stops when x gets to 3. Once again, if we integrate the function 1, we'll be integrating 3 minus square root of y, and that will give us the area above the square root and below the x equals 3. How's everybody okay? All right. Next one involves the circle. Let's suppose we have the circle x squared plus y squared equals r squared. So we got a circle of radius r. So now that we have this, the equation for a circle is x squared plus y squared equals r squared. We know that we can't write y as a function of x. We know that we can't write x as a function of y. Because the plus or minus shows up when we're solving for either one of those variables. So if we solve for y, if we write y equals plus or minus the square root of r squared minus x squared, we get two functions. The same thing happens if we solve for x. We get two functions. I spelled y wrong. How many x's are in y? I think it's still 0. So we can't write one function, write y as a function of x or x as a function of y. We need two, because the circle fails the vertical line test and the horizontal line test. But the plus and minus describe the two halves of a circle. For y equals plus or minus the square root of r squared minus x squared, the plus square root is the top half, minus square root is the bottom half. So plus is the top half, and the minus is the bottom half. So there's the plus and the minus. The same thing happens with x, but x has different positive and minus. It's not up and down. X is measured left and right, and positive is the right half. And negative is the left. So if we wanted to describe this circle as a double integral, so we're going to integrate some function over this region R, which is a circle of radius little r. We're going to want to be able to do this as a dy dx integral. And as a dx dy integral. So we need a few more details. If this is a circle of radius little r, then at this point we're at R0, going around the circle. Here we'll be at 0r. Going back to this end of the circle, we'll be at negative R0. And then down here at the bottom, we'll be at 0, negative r. So in the dx dy, in the dy dx integral, the x's, dx integral is the last integral. So we have to say what x is between. And the x's go from negative r to r. Then we could pick a typical x value and say, what is y between? So the bottom is going to be the negative square root, and the top will be the positive square root. So we'll integrate from negative square root of r squared minus x squared to positive square root of r squared minus x squared. Y goes between the bottom half and the top half. X goes from negative R to R. That gives us the whole circle. Switching things around. If we have a dx, dy, now the y has to be between constants, and y is going through between the same constants, negative R to R. So I'll put those first. And then the x, we have to list from left to right. The left half is negative square root of R squared minus Y squared, and the right is positive square root of R squared minus Y squared. So each of these double integrals will integrate over this region, everything inside this circle. Two ways to describe this region R in a way that our double integral will understand. We can integrate this, integrate the function 1 to see if it will give us the area of a circle. So if f of x, y is equal to 1, then we integrate y and we get positive square root minus a negative square root. So we get 2 square roots of R squared minus X squared, and then we evaluate that from negative R to R. If we want to do that by hand, then we're going to have to grab ourselves some trigonometric substitution, or we could run it through a machine. Any questions? Everybody remember trigonometric substitution? Good, because then we don't have to do the trigonometric substitution on this problem. We'll all just trust each other that we've done trigonometric substitution and we don't need to have it done again. Any questions? Mostly because I'm worried about how y'all are taught to do trigonometric substitution. Actually, I'm more worried about how you integrate even powers of cosine. I'm worried that you use parts. That kind of bothers me. Any questions? Let's suppose that we had parts of the circle. That we just wanted some parts of the circle. Let's suppose that we want to describe the part of the circle in quadrant 4. So let's say that another region . So what if our region was just the part that was in the 4th quadrant? Still a circle, but just this part. We don't want to integrate over the whole circle. We just want to integrate the part that's in quadrant 4. And as usual, we want to set up 2 double integrals to describe it. Oops. So let's do these 2 double integrals. The first is a dy dx. The x has to go between constants. And now that I've limited myself to the 4th quadrant, x is going to start off at 0 and go up to r. X still has to be constants. So we'll go from 0 up to r. Now for the y's, if we pick a typical x value, we need to find the bottom y value and the top y value. The bottom y value is going to come from the bottom half of the circle. So negative square root of r squared minus x squared, but it'll stop at 0. Now we can integrate f of xy over these values. If I want to describe this quarter of the circle in a dx dy, now y is going to take the role of the ones with the constants. The y starts off at negative r and stops at 0. And then the x starts off at 0 and goes up to the right half of the circle. So we control what goes into the f of xy dy dx or f of xy dA by describing what x goes between and what y goes between. That was backwards. What x goes between and what y goes between. The function is just going to be the height above each dA. Any question? How's everybody okay? So, to describe a double integral, we're just saying what values of x and y are we plugging in? What's x between and what's y between? And we can just do this in pieces. I never justified us being able to do iterated integrals like this. I just said that we can do it, and you all believe me. This is probably because I have too much power in this little dynamic here, because I just like say math stuff and then write some symbols. Everyone's like, oh, all right, that sounds reasonable. Even though it sounds reasonable and trust in someone are a very weak basis for a belief system. You know what I mean? Sounds reasonable, it's terrible. So we got good news and we got bad news. The good news is that we can expand this out to triple integrals using the same kind of thinking. We just have to add one dimension to everything. The bad news is we kind of stop at triple integrals, because once you can do triple integrals, then anything after that is just adding more stuff, because we do the same thing. Double integrals, significantly different than our simple integrals that we had in Calc 2. The only thing we were ever plugging in for a definite integral in Calc 2 was an interval from A to B. There's no effort in describing that. Double integral has all this stuff because a two-dimensional shape can have all kind of shapes. It could be a circle, it could be a square, a triangle, one side could be a parabola. I could have put one parabola going one way and another parabola going the other way. Lots of different ways to make a shape in R2. So we had to get the concept of what's x between and what's y between. Now we need to see how far, what happens if we do a triple integral. What are we thinking of, and what are we going to have to do? If you guess the same thing, then you're right. Let's talk about triple integrals. So a triple integral you should not be surprised. We're going to have a function of 3 variables. We have now jumped up into R4. So welcome to 4-dimensional space. We're going to talk about it in equations, so we don't have to think about it. It's going to be hard to think about R4. So W is going to be a solid in the X, Y, Z space. So W is a three-dimensional solid in four-dimensional space. Just like R was a two-dimensional set in two-dimensional space. So W is a three-dimensional subset of three-dimensional space. So W is a solid. W is a three-dimensional solid. This makes sense because W is presumably all the things that I'm going to be plugging into my function, and my function has three variables. So I can only plug things in that are ordered triples, X, Y, and Z. That's what this function needs. Whereas, so now we have to go to the dx parts. In a simple integral, the dx was just some small piece of an interval. In a double integral, the dA was some small rectangle in the plane. So for a triple integral, we'll have some small piece of volume, dV. So dV is going to be some small volume, some small cube piece of W. So dV is some small cube in W, just like dA was some small square in R, just like dx is some small interval in the interval from A to B. Still the same thinking going backwards. We're going to have to find a way to describe. We're going to have to find a way to describe the values that we need to plug into the function. And we're going to use the same technique that we used for the double integral. I'm going to need three integrals. And I'm going to need to describe what's Z between. So if dz is the first one, then I'll have to say what Z is between. Then I'll have to say what's Y between. Then I'll have to describe what X is between. Just like with double integrals, the last integral, the outside one, is going to have to just be between constants. Now I've got two earlier integrals. These can be these endpoints can be functions of upcoming variables. So y can be between functions of x, not z, because z is already passed by. Once we integrate dz, we're done with z. Z is gone. We only have x and y. But in the double integral dy dx, y can be a function of x to another function of x. I think I was using g for these. So g1 of x, g2 of x. Now this first integral is z, and that can be a function of two variables, because there is x and y still coming up after the dz integral. So z can go between functions of upcoming variables. And there are two. The early integrals can be functions of upcoming variables. The last integral must be constants. So once we see how this works, then we don't have to stop and do fourth integrals. What's after triple? Home run? I don't know. But if that's 4, what's 5? What if in baseball, when you cross home, instead of that being the end of it, you just like turn and go to first if you can make it? Just keep going around. Anyway, what are we talking about? Oh, yeah. So if I had a fourth, so instead of dz dy dx, I had say w dz dy dx. Then the w's can be functions of 3 variables, x, y, and z. So it's easy to stack more integrals if we have higher dimensional things. Questions? So, for example, oh, and the other thing we want to mention here, just like the integral of 1 dx is the length of the interval, just like the integral over r of 1 dA will be the area of region R, the integral over W of 1 dV will give us the volume of the solid W. If we go to a fourth dimensional thing, integral over, I don't know, F for fourth dimensional of 1 dH for hypervolume, that will be the four-dimensional volume of whatever I said, the four-dimensional solid. So it just keeps on going. Integrating 1 gives you the size of the stuff that you're plugging in. All right, let's look at an example. So if W is a rectangular solid, X goes from 0 to 3, Y goes from 0 to 4, and Z goes from -2 to 0. If we wanted to just integrate a function of 3 variables over this solid, then we would set up a triple integral. Oops. Triple integral. Spelled comma wrong. Parentheses is a capital comma. So let's set up a dz dy dx integral. Just like our intervals, just like a rectangular region for a double integral, rectangular solids going to be the easiest triple integrals that we can set up. The first question we have to ask is what's z between? It's always between the constant -2 and 0. So we just integrate z from -2 to 0. The y's we integrate from 0 to 4. And the x we integrate from 0 to 3. So we can see that the volume of the solid over which we're integrating is 3 times 4 times 2, so 24. If we integrate the function 1, that should give us the volume of the solid, give us 24. Let's find out. So if we do the integral from 0 to 3, from 0 to 4, and from -2 to 0, the function 1, dz, dy, dx. First integral is the dz integral. The integral of 1 dz is z. So we get z evaluated from -2 to 0. We still have two integrals, from 0 to 3 on the x and from 0 to 4 on the y, with the dy integral on deck. Z evaluated from 0 to -2 is going to give us 2. We know that if we integrate the function 1, a double integral to function 1, that gives us the area of what's left over. We can see the area coming up as 12. And there's that 2. 2 times 12 is going to be 24. So looks like things are going to work out. But if we integrate 2 dy, we end up with 2y. Evaluated from 0 to 4. And we still have the dx integral to go. So here we got 2 times 4 minus 2 times 0, which will give us 8, and that'll give us our last integral from 0 to 3 of 8 dx. The integral of 8 dx is just 8x evaluated from 0 to 3. Questions? Triple integral of the function 1 dv will give you the volume of W, the solid over which you are integrating. At this point, it's kind of hard to picture what's going on. We have a 4-dimensional volume because we're taking a 3-dimensional volume in dv and multiplying it by some other length. So it's a 4-dimensional volume. So it's hard to think of the volume, the 4-dimensional volume, underneath the function of 3 variables, which would be a solid in R4, a 3-dimensional solid in R4, and above the solid W. But once we start getting into the equations, we can see that this is a 4-dimensional that we can calculate in higher dimensions without having to picture what things look like in higher dimensions. Questions? Comment? This is the goal, to look at equations and symbols and integrals and be able to and know what those things should look like, so that when we are unable to make pictures, we can still see how where these 4-dimensional things come from. We can still see how to picture them, even though we can't see them in their full 4-dimensional glory all at once. Question? Comment? Snide remarks? So like we said before, you got to be able to do this forwards and backwards. I have to give you a region and you write double integrals, and I have to be able to give you a double integral and you draw the region, and then reverse the order of integration. So that's going to be our game for tomorrow. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.